Assalamu alaikum, dear students. Today we shall discuss another type of oxidation, that is using selenium dioxide. In organic chemistry, while we are discussing the oxidation reactions, you should remember the reagents that are specifically used for the oxidation. I have tried my best to explain those reagents which are very much basic, so they are very much useful, so you should remember them. Now today we shall talk about the oxidation using the selenium dioxide. uh, this I am drawing another reaction, so it will explain you the use of this selenium dioxide. This is cyclohexanone. When cyclohexanone is made to react with selenium dioxide in the presence of slightly basic solution, what happens? The alpha carbon of the cyclohexanone gets oxidized into keto group. Here we had methylene group having 2 hydrogen atoms. So upon oxidation with selenium dioxide, it changes into ketonic group. This is cyclohexane 1,2 dione. So this reaction is used to oxidize the methylene group that is adjacent to keto group. Let's draw another reaction. I have drawn here an alkene that is cyclohexene. These two carbons that I am going to make them steric to differentiate. These two carbons are called allylic carbons. Allylic carbons, and these two carbons that have olefinic double bond, these carbons are called vinylic carbons, and these two carbons and this carbon, these three carbons are called allylic carbons. So when those compounds containing allylic carbons, they are made to react with selenium dioxide followed by hydrolysis, they prepare allylic alcohols upon reaction with the selenium dioxide. Similarly, active methylene compounds, I am drawing here an active methylene compound, that is ethyl acetoacetate. Ethyl acetoacetate. Upon reaction with selenium dioxide in the presence of a base, what happens? The active methylene that is adjacent to 2 electron withdrawing group, this carbon gets oxidized into another keto group. So we summarize this as selenium dioxide oxidation actually makes the oxidation of alpha carbon, oxidation of allylic carbon, and it also can be used for oxidation of active methylene compounds. Now let's discuss the mechanism of this reaction, and that mechanism will guide us to many problems. Mechanism. Actually, selenium dioxide in the presence of water, it changes into selenious acid. This is selenium dioxide. And what is this? This is called selenious acid. Let's take a ketone, simple ketone, that is cyclohexanone. And we know that selenium dioxide, upon reaction with cyclohexanone, it converts the methylene, the carbon that is adjacent to keto group, it will get oxidized into carbonyl carbon. So what happens? First, in the acidic or basic medium, this changes into enol. So enolization occurs in the first step. Enol is formed, and you know that enolization is a reversible reaction. Predominantly, cyclohexanone remains about more than 99% in this form, cyclohexanone. But when in the presence of acid or base, this enolization reaction occurs. So we get this enol, and this enol reacts with selenious acid like this. This OH, this attacks on this selenium because it's an electrophilic center attached to three highly electronegative elements. So it contains some partial positive charges. So this oxygen attacks on this selenium, and this hydroxide leaves. So you get positive charge on oxygen, selenium, OH, double bond O minus hydroxide. This oxygen is containing positive charge. It is electronegative element having positive charge, so it makes it very less stable. So what it does, it pulls the electrons towards itself. So what happens, minus hydrogen ion, so you get this intermediate O selenium. What is the name of this compound? This is another selenious ester. Selenious ester. Then in the next step, 2,3 sigmatropic rearrangement occurs. 2,3 sigmatropic rearrangement. I hope you have understood the sigmatropic rearrangement. Probably you have gone through these course about the rearrangements in organic chemistry, like pinacol rearrangements, benzylic acid rearrangements, and this is another type of rearrangement that is called sigmatropic rearrangement. What is this 2,3? Actually, it designates the bond that is going to rupture. Here you can see when this bond that is between oxygen and selenium, it ruptures, this bond moves here, and this through this carbon attacks on this oxygen, and this bond moves on selenium. This is very much important reaction step. What happens, the bond between oxygen and selenium, this moves here making double bond over here, and this bond attacks on this oxygen, this bond moves over the selenium. So you get migration so you get the migration of the selenium from oxygen to the carbon. So migration of this group occurs from oxygen to this carbon. And look, why do we call it 2,3 sigmatropic rearrangement? So you should number the atoms starting from this bond that is going to break down. So let's number it: 1, 2, 3, 1, 2, 3, and here 1, 2. So you are going to make a bond between 2 and 3. So this is why this is called 2,3 sigmatropic rearrangement. And what happens in the last step? The base, because this reaction is occurring in the presence of base, this base abstract this hydrogen. This base attacks on this hydrogen, and this bond moves here, this bond moves here, and hydroxide ion leaves. So you finally get selenium plus hydroxide. What is the oxidation state of selenium here? 0. And what was the oxidation state of selenium in the start? Here it was +4. So it means the selenium has reduced and it has oxidized the other compound. In the start, in the start of this reaction, we had no oxygen at the methylene carbon, but in the final product you see that this methylene group has changed into a keto group. So you have obtained cyclohexane 1,2-dione. I repeat this mechanism again, so it will be better for you to get some point here. In the first, selenium dioxide, in the presence of a solvent, that is water or a base, it changes into selenious acid. And in the presence of a base or of acid, this ketone usually changes into its enolic form. So enolization occurs, and that enol reacts on this selenium, leaving hydroxide ion. So you get selenious ester. And when you get the selenious ester, it undergoes 2,3 sigmatropic rearrangement, where the bigger group migrates from oxygen to the methylene carbon. In the final step, hydroxide or the base abstract the hydrogen that was the second alpha hydrogen that was attached to the alpha carbon. So base removes this hydrogen, this bond moves here, this bond moves over here, and hydroxide and leaves. So you get keto group at this previously present methylene group. So we get this compound. So this is actually the this was the mechanism for the oxidation of the methylene group adjacent to the keto group. For your better understanding, I draw another reaction. Selenium dioxide in the presence of base. So what do you expect? What would be the product of this reaction? We know that selenium dioxide oxidizes the methylene group that is adjacent to the keto group. Now here we have two carbons, but this is not a methylenic carbon. It does not have any alpha hydrogens. So this carbon will get oxidized and you will get this product. So what happens in this reaction? You get 1,2-diones. Similarly, in previous example we got cyclohexane 1,2-dione. So 1,2-dicarbonyl compounds are formed by the reactions of the ketones with selenium dioxide in the presence of base. I'm writing another example. Selenium dioxide in the presence of a base. What would be the product? So you should remember that selenium dioxide actually oxidizes the alpha methylene group. Here we have two alpha carbons, but this alpha carbon is not methylene group, it's a methine carbon, but this is a methylene carbon, so you will get this product. This would be your final product. Let's I'm drawing another structure. Now this is very important. Where would be the reaction occur? Now we have two methylene groups here, but you should know that this methylene, the approach of selenium dioxide to this methylene group would be difficult owing to the presence of this methyl. So the transition state where the selenious ester would be formed, that will be statically hindered with this methyl group. So oxidation of this methyl group, methylene group, will be in a predominant amount. Similarly, this selenium dioxide is used to oxidize the methylene group of the active methylene compounds. Oxidation of active methylene compound. In the presence of selenium dioxide, in the presence of a base, you get this compound. Let's draw its mechanism. What happens in the first step? We know that in the presence of a base or an acid, enolization occurs. What is enolization? The migration of this acidic hydrogen to this oxygen. That will attack on the selenious acid. Selenious acid. How? It will attack on this electron deficient selenium, leaving hydroxide ion. So you will get since the oxygen is now bearing a positive charge, making it unstable. So when this hydrogen leaves, you get this. I'm drawing the last structure again. Now what will happen? 2,3 sigmatropic rearrangement will occur. 2,3 sigmatropic rearrangement will occur. How? The bond between selenium and oxygen, this bond will rupture. How? This bond will move here, and this bond will attack on oxygen through this carbon, and this bond will move on selenium. I repeat again. The bond between oxygen and selenium ruptures, and this bond moves here between carbon and oxygen, making double bond here. This bond through this carbon attacks on this oxygen, and this bond moves over selenium. So you get this another intermediate where the migration of this bigger selenium hydroxy group has occurred from enolic oxygen to the alpha methylene carbon. What will happen in the next and the last step? The base will abstract this hydrogen. This bond will move here between carbon and oxygen. So you will get selenium plus hydroxide ion. So you see here this carbon that was initially methylene group, now it has now oxidized into keto group. So selenium dioxide is used for the oxidation of the active methylene compound, and specifically the oxidation occurs at the methylene carbon to convert it into a keto group. This step is very important. In the first step, the enol react with selenious acid and the selenious ester is formed. In the next step, the 2,3 sigmatropic rearrangement occurs. Now, why do we call it 2,3 sigmatropic rearrangement? You will have to designate the atoms by numbering 1, 2, 3. 1, 2. So 1, 1 atoms, the bond between the 1, 1 atom is going to break down. And where is the new bond is going to be formed? Between 2 and 3 atoms. So that's why we call 2,3 sigmatropic rearrangement. So after 2,3 sigmatropic rearrangement, you get the migration of this selenium group, the bigger group, from oxygen, enolic oxygen, to the methylene carbon. And in the final step, the hydroxide ion actually abstract this hydrogen. This bond moves here, making carbon and oxygen double bond. This bond moves over selenium, and this bond moves over the hydroxide ion. So hydroxide ion leaves as OH negative. So finally you get the oxidized active methylene compound. And in the last but not the least, this selenium dioxide is used for the oxidation of allylic carbon. Oxidation of allylic carbon using selenium dioxide. Let's we have this alkene, that is propene, and you are going to react it with selenium dioxide followed by hydrolysis, not using base, followed by hydrolysis. So what happens? You get what do you get? You get the allylic alcohol. So in this case, this allylic carbon, this carbon is allylic, and these two carbons are vinylic. So allylic carbon is changed into an alcohol group. So you get allylic alcohol. Let's see how. We discuss the mechanism. We know that in the presence of some solvent like water, little bit ionization occurs. This bond moves here and it will attack on this selenium dioxide. So you will get this compound, this intermediate. It will abstract proton from the solvent, so you will get here OH. This oxide, when it will abstract this proton, it will change into hydroxide ion. Can I draw this like this for the better understanding? I have just written this selenium double bond oxygen from this direction to here and hydroxide to here. Now what happens in the next step? 2,3 sigmatropic rearrangement occurs. How? The bond between selenium and carbon, it going to rupture. When this bond moves here, this double bond attacks on this oxygen and it moves over this selenium. What you get? You get this compound. And why are we calling it 2,3 sigmatropic rearrangement? Let's number this carbons 1, 2, 3, 1, 2, 3, and 2 and 3 atoms are going to make a new bond, new sigma bond. So that's why we call it 2,3 sigmatropic rearrangement. And what happens in the last step? Last step, just the hydrolysis occurs. This hydrogen attacks here, this hydroxide attacks here. So finally you get this compound, allylic alcohol and selenium dihydroxide. You see here, allylic alcohol is formed. So allylic carbon, that this allylic carbon upon oxidation with selenium dioxide, now it has changed into an alcoholic group. So allylic alcohols are obtained when alkenes, allylic carbon of the alkene is reacts with selenium dioxide followed by hydrolysis. Here you should remember few things. Number one, selenium dioxide followed by hydrolysis. What will be the product? We know that in case of alkene, allylic carbon are going to hydrolyze, or you can see the changing into an alcohol group. We'll have to find out where are the allylic carbons and how many allylic carbons are there. This is an allylic carbon, this is also an allylic carbon, and this is another allylic carbon, and hydroxylation will have to occur at one of these allylic carbon. And where would be the hydroxylation would occur? Remember, if the allylic carbon is a part of cyclic system, like these two carbon are the part of this cyclic ring, hydroxylation will occur at these allylic carbon. Now we have in competition of two allylic carbon, and where probably the oxidation will occur. Remember, those allylic carbon that are more substituted. You see, this olefinic carbon is attached to two allylic carbons, and this olefinic carbon or vinylic carbon is only substituted with one methylene group. So this allylic carbon is more substituted. So that's why allylic hydroxylation will occur here. I write here more substituted alkene allylic carbon. I should write allylic carbon of more substituted alkene will get oxidized. You should remember this principle. And here now we had two allylic carbons that were more substituted. So remember that allylic carbon that is the part of a cyclic system, it will get oxidized. So that's why the reaction occurs here. I'm writing another very important example. This is an alkene, selenium dioxide followed by hydrolysis. What would be the product? We know that allylic carbon will get hydroxylized, will get hydroxy group. Now, which allylic carbon? First, you will have to recognize where are the allylic carbon and how many are there. We have now one allylic carbon, there's one allylic carbon, there's one, and one allylic carbon, there's one. We know in the previous example that those allylic carbon will get oxidized that are more substituted. Here this carbon has two allylic carbon and this carbon has only one allylic carbon. So among these two allylic carbon the reaction will occur. Now whether the reaction will occur here or the reaction will occur here. So remember again another principle. The hydroxylation of the allylic carbon will follow the E-selectivity rule. E-selectivity rule. And what is E-selectivity? When the hydroxylation occurs at this allylic carbon, you get a trans product. Is this trans product? Yes. How? Let's see. Let's prioritize these two groups. It will get number 1, it will get number 2, and this one number 1, number 2. So on the basis of priority we have given them the numbering. This group is having the higher priority as compared to this group, so I am designated as 1 and this will be numbered as 2. On the priority basis the methyl group is more superior than the hydrogen, so I am going to number it as 1 and 2, and 1 1 are across each other, across the double bond, so this is the E product. So the E product will be predominant. This will be your final product and this product will not be formed. Why? Actually when the selenium dioxide reacts and a migration occurs, and the migration is more favorable when selenious ester is formed on that allylic carbon that is across or opposite to the other group. So that's why the E product is formed. Very important to remember. This is called the E-selectivity principle. I'm writing here the last example and you should tell me what will be the product. Selenium dioxide followed by hydrolysis. Now in this compound we have two olefinic double bond. So which olefinic double bond is more substituted? Here you see that this olefinic double bond has two more substituted olefin. It has two methyl group while this carbon has only one substitution. So these are two allylic carbons and hydroxylation has to be occurred at one of this position, and where you after the reaction, I'm not drawing the complete mechanism. If the hydroxylation occurs here, you will get this product. And if the hydroxylation occurs here, you get this allylic alcohol. Which product will be predominant? Remember the E-Selectivity Principle. Which is the E product? Let's number these two groups first. This group is more has more priority and as compared to this, and here we have the hydrogen, so this will be the 1 and it will be the 2, so 2 2 or 1 1 are across each other, so it's a E product and it will be the major one and the final one. I hope you would have gone through this oxidation very well. Remember, selenium dioxide is used to oxidize the alpha carbon adjacent to carbonyl group, that is keto group. And this selenium dioxide also can be used for the oxidation of the methylene group of the active methylene compound. And this selenium dioxide, using when it is hydrolyzed, selenium dioxide followed by hydrolysis, it actually converts the allylic carbon into allylic alcohol, and where we learned that more substituted olefinic double bond will actually direct the hydroxylation of the allylic carbon. And then we learned the E-Selectivity principle. Thank you so much.